Hello everyone. In our today's discussion, we are going to study some basic operations on signals. Okay, so let's go ahead. Now, in our previous video, we have studied about signals. We have studied some basic idea about the systems as well. So now let's understand what are the various operations that can be performed. So the most important objective of a system is to use or manipulate the signal. Okay. Now, usage and manipulation of signal involves certain operations. So these operations can be performed on dependent variables or operations can be performed on independent variables. So now let us discuss both of the cases one by one. First of all, operations performed on dependent variables. So this includes amplitude scaling, addition of signals, multiplication of signals, differentiation, and integration. Similarly, operations performed on independent variables, it includes time scaling, reflection or time reversal, or time shifting. Okay, so we will discuss these points one by one, and we will try to understand the practical, usage of all these activities. Because you know very well that objective of this study-based technologies is to make you aware of how you can apply engineering in actual environment. Because I'm sure you know very well, guys, being an engineer doesn't mean that you are going to work in some bank or you have to work in some IT company for production support kind of environment. No, that may be your job. That's what you are getting after the completion of your engineering. But the actual purpose of engineer is to build things. And in order to build things, you need to have in-depth knowledge of all these operations and how they can be implemented in a practical environment. Okay, remember that engineering doesn't mean that you have to go ahead and learn some formulas or learn some theorems and so on and complete your assignments or pass your semester exams. No, it is related to how you are going to implement the knowledge that what you are getting in an engineering college into the real life environment. Okay, so let's go ahead and try to understand this. The first objective is amplitude scaling. So in our previous video also, you have seen some idea about continuous time and discrete time signals. Okay, so you can see here that xt and xm, these are continuous and discrete time signals respectively. Fine. Here, the c, whatever you can see here, is your scaling factor. Okay. Now, you can see here in the below figure that this is a square signal over here. It's ranging from -2 to +2, and its amplitude is +1. And once you perform this amplitude scaling, it goes to 2 in your y direction. Okay, this is one example of your amplitude scaling. And how it is used? It is actually used in your electronic amplifier. Fine. So you can understand here, like in the case of an amplification function, wherever you are going to use, to amplify your sound or increase the signal amplitude and all. So therein you can go ahead and work it as a amplitude scaling. Okay. In a similar manner, we have something called as addition. That is addition of signals. Again, in terms of continuous time, it may be x1t plus x2t. And in discrete time, it may be x1n plus x2n. It looks something like this way. Let's say this is your first wave or first signal. You are going to do some kind of addition and you are going to add it to the another wave or another signal. So this should be kind of your output, right? You're just adding two different signals over here, and its usage is audio mixture, right? This combines your music or voice signals. I'm sure so most of you have seen DJs and all, right? So what they do, they just use the mixers and they just mix different sounds and then they produce a new or different kind of sound wave, right? So that is the usage of your addition in case of audio mixer. Okay. Similarly, something about multiplication. Again, this multiplication, it involves output signal to be equal to your x1t dot x2t. And in terms of discrete time, this is x1n dot x2n. Okay, so this again, the output yt is given by the product of corresponding values of the concerned input signal. So let's take an example over here. You can see I'm taking a discrete time or a continuous time example like that actually. So this is your first signal. You can see here. We are going to multiply it with this pulse over there, right? And this should be the output of the product of signals, right? So this is how actually it looks like, and the usage for the same is amplitude modulated radio signals. Here X1T consists of audio signals plus a DC component, and X2T signal is called as carrier wave, which is basically sinusoidal in nature. Okay, so the thing is like this kind of scenario we can use in your modulation purpose, right? So modulation, of course, you will study in communication class as well. You might have studied it, or we'll have a dedicated lecture for the same. Now, guys, as I just said, like your X2T may be your carrier wave, and that should be sinusoidal in nature in case you are using it in amplitude modulated radio signal. So the question comes in our mind, like why do we use sinusoidal signals? The reason is the sinusoids play a key role in audio processing because if you shift one of them left or right by any number of samples, I will study about shifting as well in our coming points of this session only. So you get another one. All right. At the moment you just shift one or two samples either left or right, you will get another one actually. And this makes it very easy to calculate the effect of all sorts of operations over the sinusoids. Our ears use this same special property to help us pass the incoming sound. That is why the sinusoids and the combination of sinusoids can be used to achieve many musical effects. Okay? So that is one of the reasons why do we use sinusoidal signals as a part of a carrier wave, and why do we use it actually in our signal systems environment also. Now, as for the next step, we have something called as differentiation. Okay? So differentiation is again the output signal is actually the differential of the input signal. Right? So you can see here in this below diagram that there is a signal. You can see here linear kind of signal, linear kind of function, a ramp here or there out of this differential signal over there. I mean this is a root raw signal actually, and we have to differentiate it. Okay. So once you go for the differentiation, this will be the final output. Right? This will be the final output of that comes after the differentiation. Right? Now, let me show you some examples for the same. First and most important example is your inductor. Right? Let's say you apply some voltage at this terminal, and whenever you apply a voltage, the current will develop and will start flowing through the inductor, right? And this voltage is given by L as a constant, that is the value of the inductor, and di by dt, that is the differential of your current. Fine. So now if you have got some idea about the differentiation, now the point is like we need to understand some use cases like where we can apply these differential signals actually, right? Where do we have to use? So the thing is like in this case, in this example, I will show you like how you can use this differential signal in case of thermal analysis or even chemical analysis, right? Again, my objective is to make you understand that it is your responsibility, being an engineer, it is your responsibility to apply your knowledge in real-time environment. Okay? It's nothing like you have to just cram some formulas and understand some kind of theorems, and then you have to appear for some competitive examination and then follow the same trend actually. Right? You are an engineer, you are supposed to build something. Okay, so let's go ahead and try to understand about this differential part first of all. So differentiation practical example, first of all, if we talk about, there are two scenarios that we will discuss over here. You might have heard about first derivative, second derivative, third derivative, and so on. First derivative is something like dy by dx, then d2y by dx square, then d3x by your dx cube, something like that actually, right? And the order continues like that. So the higher orders we will discuss somewhere later on as well, but the most important point that we need to discuss is first and second order derivative. So first of all, what does it mean by first derivative? First derivative, that is dy by dx, is basically rate of change of y with x, which is actually interpreted as slope of the tangent to the signal at each point, right? Let's take an example. Let's say this is your signal, right? And each and every point, what is the slope, right? What is the slope of the tangent, right? Slope, I'm sure all of you know very well. Those who have studied mathematics in 11th and 12th, I'm sure all of you have done it, and some of you remember that as well, right? Slope is nothing but tan theta, right? So y equal to mx plus c, where m is a slope. Fine. So okay, we'll go ahead later on. About the second derivative, it's again, this is a derivative of a derivative, which is basically the measure of the curvature of the signal. That is the rate of change of the slope of signal, the rate at which the slope is actually changing. Okay. So the first example that I'm going to discuss over here is your amperiometric titrations, thermal analysis, and kinetic experiments. So under these, a series of straight lines segment of different slopes are generated. You can see here, if you can look at, to some extent in a broader view, actually, you can find that this is not a complete straight line, actually. Right, this is just broken down somewhere and somewhere and something like that, actually. Right, so this is what the practical, case you'll feel. You'll find out during your industrial setup, actually. Right. So the objective is to determine this how many segments there are, where the bricks between the fall and slopes of each segment. And this is very much difficult to do from the raw data because the slope differences are very small and the resolution of the computer screen display is limited. Right? So the task is much similar if it's very much similar if the first derivative, that is slope of the signal, is calculated, right? Now you may see in the second graph that, the first graph actually, that each signal is clearly seen as a separated step whose height is the slope, like this. Both second and first graph, you can check it out, right? So now the thing is like, note that in this example, the steps in the derivative signal are not completely flat, indicating that the line segments in the original signal were not perfectly straight. This is most likely due to random noise in the original signal. And although this noise was not particularly evident in the original signal, and it is more noticeable in the derivative, right? So I hope now you can understand the use of this differentiation, right? This is the basic differentiation of a signal. You can see here that basically it's quite difficult for us to find out the breaks. But once you differentiate the given signal, you have seen this differential output. Now you can clearly define the signal, right? This is related to your thermal analysis. Now let's take an example for chemical analysis. Right. It actually employs a very classical use of second differentiation. Right. So in most of these titrations, we are going to study about this titration setup. The curve has sinusoidal shape and the end point is indicated by the inflection point. Okay. The point where the slope is maximum and the curvature is zero. That is called as inflection point, right? So the first derivative of the titration curve will therefore exhibit the maximum at the inflection point, and the second derivative will exhibit a zero crossing at that particular point. So the maxima and zero crossings are usually much easier to locate precisely than inflection point. You can see here that the first window over here is the first derivative and second window over here is the second derivative of the signal. So let's take an example, like figures over here shows the iteration curve for the pH of very weak acid with a very strong base with volume in milliliter on the x-axis and pH on the y-axis. Here the volumetric equivalence point, that is theoretical endpoint, is around 20 milliliter. And the end point is a point of greatest slope, which is also called as inflection point, right? Where the curvature of the signal is zero. With weak acid, it is difficult to locate this point precisely from the original titration curve. And that is the reason we are using the second derivative over here. Now guys, you can understand that if you are building some equipment or some product, right, which is supposed to be used in case of chemical analysis, I'm sure now you are getting some idea of the circuit in your mind, right? That is the different thing. But the point is like what you need to understand is how you are going to use the signals which are generated by a particular sample or whatever the subject, right? If something is generating a signal, how you have to manipulate it, how you have to use it, that you need to understand, right? So you can, I'm just giving you an overview like how and where you can apply your knowledge of engineering into different levels of fields. Fine. So here we have employed this signals and system capability to work on the kinetic analysis, thermal analysis, and chemical analysis over there. All right. Now let's move further. It's something about integration. Now about this integration, let's say this is our raw signal or the source signal. Once we go for the integration, you can find that this kind of output, right? The thing is like, again, let's see, the most popular source of this integration signals is a capacitor that you can find in almost all kind of books, right? What you will not find is the practical applications, right? So let's see that. Again, you are applying a voltage on these terminals. The current will develop over there, and now you'll find out that the relation, how this voltage can be used or can be identified by integrating the current over there. IC is a current flowing through capacitor, and VT0 is the initial voltage at time t equal to 0. Okay, the most popular usage of this integration is for analog to digital conversion, right? Even then, if we talk about the real-time scenarios as well, you can integrate a signal representing the water flow, producing a signal representing a total quantity of water that has passed by the flow meter. And this application of an integrator is sometimes called as totalizer in the industrial instrumentation trade, right? So this is how you can use the integrator circuit as well, that how you can design an integrator circuit. There are different ways. You can use op-amps as well. So that we will discuss in basic electronics classes also. Fine. So now let's move further. We have already studied about operations on dependent variables. Now it's our task to study of the operations over the independent variables. Okay, so let's start it. So first objective is your time scaling. Now again, you can see here that we have a continuous time and discrete time signal. Let's move further. This A or K, whatever you can see here, is basically your scaling factor. Now, first case, that is A is greater than 1. In that case, your signal will be compressed version of original signal. Okay, will get compressed. I'll show you an example also. Case number 2, like if A is less than 1, in that case, your output signal will be expanded or stretched version of your original signal. Fine. Similarly, in terms of discrete time signal, it is valid only for the integer values of k. And if k is greater than 1, like then some values of the discrete time signal are lost. Fine. Let's say this is your original signal. You can see here a triangular signal over here, and now if, as I have already explained, if A is less than 1, let's say this time A is equal to 1 by 2, then xt by 2 is, it should be the stretched version. You can see here now your signal has been stretched from -2 to 2. And similarly, if A is greater than 1, then this time A is equal to 2, you can find that your signal is compressed version, right? Now, the most important implementation for the same is solar. Now, what is the solar? Solar is basically synchronous overlap add. This word by cutting the sound data into short sequences between tens to hundreds milliseconds each, and then joining these sequences back together with a suitable amount of sound data, either skipped or partially repeated in between these segments or sequences to achieve a shorter or longer playback time than original. Okay, so this is how your time scaling works, and this is the practical application as well. Similarly, it's something about time reversal. So you can also call it as reflection also. It's something like, let's say, it may be your even signal, where x of minus t is equal to x of t. It may be odd signal, where x of minus t is equal to minus of xt. That is a negative of this reflected version, right? And it is basically used for seismic source imaging. Or you can use it like if you are using for radar and sonar kind of applications, or if you are using, trying to identify the structure of earth or some material or some mineral or whatever it is. So you can, where you are expecting some kind of echo, that is your reflection part of your signals. Okay. Similarly, it's about time shifting. So let's say this about this continuous time signal, that is yt is equal to x of t minus t0, where t0 is your time shift. Okay. Now remember this point: if t0 is greater than 0, in that case your signal will get shifted to right. And in case this t0 is less than 0, in that case the signal will be shifted to left. Okay. If less than 0, it will shift to left. If greater than 0, it will shift to right. Let me give you an example over here. You can see the sample signal. This is at t minus t0. That means it has shifted to right. T plus t0, that means t0 is less than 0. It means it is shifted to left. Okay. Now about the practical application of time shifting is PVR. Right? Let me tell you about a PVR, that is a personal video recorder. So the time shifting is the process of recording and storing the data for later viewing, listening, or reading. In television, the time shifting can be done with a device called as personal video recorder, or a computer with a TV tuner card. In older times, these video cassette recorders have the time shifting capacity. Now, what are the uses or offerings from PVR? It actually offers several advantages over previous VCR technology, like your greater storage capacity, quicker navigation and program selection. It has enhanced ability to search and index programs. It's used for prioritizing of recording or viewing, and recording or viewing by the remote control over internet, right? So these are the usage of the time shifting as well. Now a question comes in our mind, like if we have a signal in a real-time environment, if we have a signal and we have to perform some mixed kind of operations, that is very obvious. In our real-time environment, it is not like we will be told that go ahead and do some shifting separately, then scaling. No, you might have some input signal and you have to use all the knowledges, whatever you are getting in some in your course or in your lectures. So let's say you have signal and you need to do both scaling and shifting. So in order to correctly obtain yt, that is the output signal from your input signal, that is xt, let's take an example. The time shifting and time scaling operations must be performed in correct order. And the proper order is based on the fact that the scaling operation is always done after your shifting. So time shifting operation is first performed over your signal. Just remember this fact. Okay. So that is all for our today's session. In our next lecture, we'll study about different elementary signals, and we'll study about the interconnection of systems as well. Right? So till then, have a nice time ahead and take a very good care of yourself. Thanks for watching our video. Please like it, share it, and subscribe it so that we can reach to larger audience and they can benefit from us. Okay then, have a nice time ahead. Bye bye.